Okay, welcome back. So what we will talk about today is more about permutations. So far what we have been interested in doing is, well, counting permutations or counting combinations and so on. Now what we would like to do is to study permutations in a in a slightly different way. What we would like to do is to try and understand permutations themselves rather than just count the total number of permutations. So recall what is an example of a permutation. So well, a typical permutation is just a rearrangement of the numbers. So let me write down an example: 516 72 348. Okay. So here is an example of a permutation of the numbers 1 through 8. Okay. Now so sometimes we can think of these as being the various positions. So there are 8 positions which we have filled with these numbers in some order. So often there are various notations which make it somewhat easier to think about permutations. So one of them is what is called the 2-line notation. So a 2-line notation, so this permutation here would be represented as follows. So we think of this first thing here as really being position 1, and the second blank here as being position 2, the third is position 3 and so on. So we think of each of them as being a certain position 5, 6, 7, 8, and then we write down what, so the first line here is the position. So in position 1, position 2, 3, 4. So we first, the top row here, the top line is just the position numbers, and the bottom line is the entry in that position. So for example, in the first position here we have the number 5, the second position has the number 1, 6, 7, 2, 3, 4 and 8. So this notation here is sometimes called the 2-line notation for a permutation. So the thing we wrote out first is often called the 1-line notation, where we do not explicitly write out the positions themselves but only keep track of the numbers in the various positions. So this is another way of representing the same permutation. Now observe, so there is also a pictorial way. You can think of a permutation as really being a function. So what do we mean by that? So imagine I have the set consisting of the numbers 1, 2, 3, 4, 5, 6, 7 and 8. So that is my set. So let me draw it as a set, and a permutation, so let me call this set as S. A permutation can be thought of as giving you a function from the set S to itself. So I have the set S to the set S. So what is this given permutation? Think of it as the first set S as sort of being like the position numbers, and the second set S sort of representing the entries themselves. So what we have is something which sends 1 to 5, 2 to 1. So let us write this out. This sends 1 to the number 5, 2 maps to the number 1. So this function sends 3 to 6, 4 to 7, 5 to 2, so 2, 3, 4 and 8. So this goes to 2, 6 goes to 3, 7 goes to 4 and 8 goes to itself. So this picture here that we have drawn is, well, another way of thinking of the same permutation. It is a function from the set 1 through 8 to itself, and further it has the following nice property that it is a one-to-one and onto function. So well, what is a permutation? So observe, a permutation of, in this example, the numbers from 1 to 8 is nothing but a function from the set consisting of the numbers 1 through 8 to itself. So let me from, it is a function from 1, 2, 3, 4, 5, 6, 7, 8 to itself, but it is more, it is in fact a one-to-one and onto function. So that's the key observation here. It's these two put together is what's sometimes called a bijection or a bijective function. One-to-one of course means that two different elements of S here don't map to the same element. So everything maps to different elements, and onto means that every single element in S here has something which maps to it. Okay, so it is sometimes called a one-to-one correspondence. Everything here maps to different things there, and everything there does get mapped from something. Okay, so it's a one-to-one and onto function, and so sometimes such diagrams are nice to have. Now one of the simplest examples of a permutation in general is what's called a cycle. So what's an example of a cycle? So let's assume we have the numbers 1, 2, 3, 4. So here's an example of a cycle 2, 3, 4, 1. So what is this? So this is the one line notation. So now I've written this out in one line notation. The same thing in two line notation would be the following. So I have 4 positions. So I have 1, 2, 3, 4. Those are the 4 position numbers. And position 1 maps to 2. In position 2 I have 3. In 3 I have 4, and 4 I have 1. Right? It's the same permutation in two line notation. And so again you could also think of it in terms of the function. So what is it from the function point of view? So I have a diagram as I did before. I have 1, 2, 3, 4, the set 1, 2, 3, 4. So here 1 goes to 2, goes to 3, 3 goes to 4, and 4 maps to 1. Okay, so those are the 3 different notations or ways of thinking about it. But in this case there is yet another thing one can do. So we have 1. So imagine what happens. So think of it from the function point of view or the two line notation point of view. Let's start with 1 and look at what 1 maps to. So 1 maps to 2, and now I am at 2 and I look at what 2 maps to. 2 maps to 3 according to this. 3 maps to 4, which then maps back to 1. Okay. So here's yet another way of thinking about or depicting this permutation. It's just something which sends 1 to 2 to 3 to 4 back to 1. Okay. So that's the reason why this is called a cycle. You can think of it most ideally as, well, numbers 1, 2, 3, 4 arranged in a circle with sort of arrows telling you. So let's assume we have to go clockwise. So it tells you which maps to which, and they sort of map to each other in a cyclical fashion. So this is why such a permutation is called a cycle. Okay. Sometimes it's called a 4 cycle to emphasize the fact that there are 4 numbers. Now so cycles themselves are a very important special case of permutations. Now let's do a more general example. So let's take the permutation which we had written out at first. So 1 in two line notation 3, 4. So here's the original example 5, 1, 6, 7, 2. 3, 4, 8, and so this was the two line notation. So let's give this permutation a name. Let's call it pi. Okay, the permutation pi does this. Now let's try and think of this in terms of cycles. Okay, so what does that mean? Let's start with the number 1. So we start with the number 1. So that's this guy, and look at what it goes to. So 1 maps to 5. So I write it in the same way. I have 1 mapping to 5. Now, well, what's next? Now that I am sort of at 5, I look at what 5 maps to under this permutation. So 5 maps to 2 under this permutation. So I note that down. Now I am at 2, so I go back to 2 and look at what that maps to. Well, it seems to map back to 1. So it looks like 1, 5 and 2, they form a cycle in this permutation. 1 maps to 5, maps to 2, which maps to 1. Okay, so that takes care of these 3 numbers. 1, 2 and 5 are taken care of. They form part of the cycle. So let's keep going. Let's look at the next number that's not in the list, which is a 3. So I write down a 3 and see what a 3 goes to. 3 goes to a 6, but then the 6 maps back to a 3. So it seems as if I have the following: 3 goes to a 6, and 6 maps back to 3. Okay, so I am also done with these two numbers, 3 and 6. Now I will look at 4, 7 and 8. I look at 4, which maps to 7. 7 maps back to 4. So I again have 4 maps to 7, maps to 4, and 8, so the last guy here, seems to map back to itself. Okay. Now this picture that I have drawn here is not that of a single cycle, but rather of 4 different cycles. Okay. So I have here a cycle of length 3. So let's keep track of the lengths of the cycles. Here I have a cycle which has 3 numbers, so I'll call that a cycle of length 3. This guy here is a cycle of length 2. This guy here is a cycle of length 2, and the last guy is a cycle of length 1. So cycle of length 1 just means it's something which maps back to itself under the permutation. So now what we have done is the following: we have looked at these 8 numbers, we have looked at a permutation of these 8 numbers, and we have what we would call decomposed it into cycles. So this permutation really is composed of, well, there is a 3 cycle, there is a 2 cycle, another 2 cycle, and a 1 cycle. These 4 cycles put together give you back this permutation. So sometimes this way of decomposing is called the cycle decomposition, and so we often have yet another notation for this. So this is called the cycle decomposition. So the notation for this is the following: the given permutation pi that we had in the beginning, we have noticed that it has the following cycles. There is 1 goes to 5 goes to 2, these form a 3 cycle. So we write this within brackets. This is to be interpreted as, well, this is just 1 maps to 5 maps to 2. This is just another way of writing it without having to write circles and so on. Now I have 3, 6, which is shorthand for 3 maps to 6 maps to 3, and I have 4, 7 and 8. So this is again shorthand for 4 maps to 7, and this is just 8 maps to itself. Okay. So this notation upstairs is just what's called the cycle decomposition of the given permutation, and the cycle structure or cycle type. So sometimes there are 2 words for this. Sometimes we call it the cycle structure of pi or the cycle type of pi is the following. It's the, you just keep track of the lengths of the cycles. So for example here there is a 3 cycle, and there is a 2 cycle, and another 2 cycle, and a 1 cycle. So we would often say that the cycle structure of pi is just the list. So what is a cycle structure? It is a list of numbers arranged in descending order. Okay, so there is, we don't really want to know the order of this. So we wouldn't want to say the cycle structure is, say, 2 plus 3 plus 2 plus 1 and so on. We are only interested in knowing what are the various lengths which appear. So we just arrange them in descending order. So we have 3, 2, 2, 1, and notice that the sum of all these numbers must always be 8, because that's the number of numbers in all, right? The total number of numbers is 8. So of course the sum of lengths of all the cycles that you get had better be 8. So 3, 2, 2 and 1 would have to add up to 8. So observe that the cycle structure always has this property, the cycle type, and so sometimes we call this, well, this is usually what's called a partition of 8. Okay, a partition, the definition is, it's a way of writing the given number as a sum of natural numbers. So what are other possible partitions of 8? Instead of 3, 2, 2, 1, you could say, for example, 7 plus 1 would be another partition, or 6 plus 1 plus 1 would be another partition, and so on. So there is a very long list of partitions of 8. This particular permutation has this cycle structure, which is, which gives you this particular partition of 8. So let's sort of look at a counting problem, which again arises naturally in this context. So it's a finer counting problem than just counting all permutations. So again we'll do it by example. So 8 is somewhat large for our purposes. Let us take just permutations of 4. So I am going to look at permutations of the numbers 1, 2, 3 and 4. Okay. Observe that the total number of permutations is 4 factorial, which is 24, but what I want to do is, we have just talked about cycle types, right. So I want to do the following. I am going to categorize them by cycle types. So I am going to make a table which has cycle types on the one hand and the number of permutations with that cycle type on the other column. So for example, what do I mean? So let me look at the following. Let me look at permutations whose cycle type is 3, 1. Okay. So I'm going to do the full list, but let me start with this. I'm going to look at permutations whose cycle type is 3, 1. So what do I mean by that? So notice that when you say cycle type is 3 and 1, what it means is I am looking for a permutation of 1, 2, 3 and 4 in which there is a 3 cycle. For instance, 1 maps to 2 maps to 3 back to 1 and 4 maps to itself. Here is an example of a permutation whose cycle structure is 3, 1, right. And well, what are other examples? So basically I need to have a 3 cycle and I need to have a 1 cycle. So how do I write down other examples? Well, first let us choose what goes into the 1 cycle. That is the easiest thing to do. So instead of 4 I could pick some other number. Let me make 3 as the element which is in the 1 cycle. Then the numbers in the 3 cycle are determined. So 3 is already done. So I need to look at the numbers 1, 2 and 4. So I have the numbers 1, 2 and 4, and how many different 3 cycles can I form with those? So for instance, I could arrange them as 1 going to 2 going to 4, or I could arrange them as 1 going to 4 going to 2. Okay. So at the moment what I have done is just write down a bunch of examples of permutations of the numbers 1, 2, 3 and 4 in which for which the cycle structure is 3, 1. Okay. Now what we want of course is to count the total number of such permutations, right. So let us try and do this. So the number of permutations with cycle type 3, 1. How do I try and count this? Okay. So here's the idea. We have already used it when trying to write down examples of such permutations. First we pick the number which goes into the 1 cycle. Okay. So first out of these 4 numbers we choose one number. So that's 4C1 ways of choosing one number. And what does this 4C1 represent? This is the number of choices for the entry which goes into the 1 cycle. So here we have just choose entry for the 1 cycle. Okay, so that is 4C1 choices. Having done that, what are we left with? We are left with 3 numbers, right? Whatever, that one number is gone and we have 3 numbers. For instance, here we had the numbers 1, 2 and 4. Now there still remains the issue of arranging those 3 numbers into a circle. Okay. So what we still need to do is the following. We need to figure out how many ways are there of arranging, say, these 3 numbers in a circle, or more generally, here's a problem that will come up when we want to do this. Find the number of ways of arranging n numbers in a circle. Let us say the numbers 1 to n in a circle. Okay. So observe here's the thing that for instance I have the arrangement 1 going to 2 going to 3 going to n going to 1. Now I will think of this arrangement as being the same as an arrangement in which I move the numbers clockwise. So when I say I want to only arrange them in a circle, what I mean is that I only want to look at the relative positions. What matters is only what's to the right of the 1 and what's to the left of the 1, not so much not so much where 1 is sitting. So for instance this arrangement here I will think of as being the same as the arrangement in which everything is rotated say by 1 unit, say the n comes to the top and the 1, the 2 and so on. This arrangement is the same as the arrangement in which the 1 is sort of at the head of a table. Okay. So now this is the usual thing of circular permutations. So how do we count this number? So the key idea is, since we don't really mind rotating all of them by some unit, here's what we will do. We will fix once and for all somebody in the head of the table. So when you have a circular table like this, think of this, the head of the table, this position, as being fixed, because I can always assume that 1, for instance the number 1 occurs at the head of the table. And why could I do this? Because since I don't care about rotating them all, I could easily rotate, if 1 isn't at the head I would rotate it sufficiently so as to bring 1 to the head of the table. Okay. Now once you have done that, the remaining n minus 1 numbers you permute them in all possible ways. So the number of ways of arranging the numbers 1 to n in a circle is in fact equal to the number of ways of, so we do the following: we fix the number 1 at the head of the table, meaning in say this top position, and just count the number of ways of permuting the remaining n minus 1 numbers in all possible ways. Sorry, the numbers 2 through n. So you permute these in every possible way, and since there are only n minus 1 of these, the total number of ways of doing this is only n minus 1 factorial. Okay. So this is what we usually call circular permutations. So we are only interested in their relative positions, and the number of such configurations is in fact n minus 1 factorial. So coming back to this problem here, we have chosen the entry which goes into the 1 cycle. What's left is 3 numbers, and those 3 numbers must be arranged in a circle, and the number of ways of doing it, as we just saw, is 3 minus 1 factorial. So it's 4 choose 1 times n minus 1 factorial, where n is 3. So what is this? This is just the number of circular permutations of the remaining 3 numbers. Okay. So we have managed to solve this counting problem. The total number of choices would therefore be 4 choose 1 is 4, and 3 minus 1 factorial is 2, so it's 4 into 2, which is 8. Okay. So the number of permutations of cycle type 3(1) is in fact 8. Now of course one wants to do it for every other cycle type as well. So observe, as we said, a cycle type would always be a partition of 4. So you could have a 3 cycle and a 1 cycle, or you could just have a 4 cycle, or you could have a 2 cycle and a 2 cycle, you could have a 2 cycle and 2 1 cycles, or you could just have all 1 cycles. Okay. So you could have, these are the various possible cycle types, and so I will just partially complete this table. So if you have so for instance let's count how many permutations would have cycle type 4. Okay. To have cycle type 4 just means how many 4 cycles are there, how many ways are there of arranging the numbers 1, 2, 3 and 4 in a circle, and we have already solved that problem. It is 4 minus 1 factorial, so it's 3 factorial, which is 6. Okay. So similarly, if I have 2 1 1 and I want to know how many ways are there of how many permutations are there with this particular cycle type, here is what you would do. You would pick, well, there are 2 1 cycles and 1 2 cycle. So let us pick the 2 numbers which form part of the 2 cycle. So once you fix the 2 cycle, the elements in the 1 cycles are automatically fixed. Okay. So the number of ways of doing this is you first pick the 2 entries which will form part of the 2 cycle. So there are 4 choose 2 ways of picking those 2 entries, and once you have picked them, you still need to arrange them in a circle. Okay. So the number of ways of arranging 2 numbers in a circle is just 2 minus 1 factorial, which is just 1 factorial. Okay. So this is again 4 choose 2, which is a 6, and so I'm sort of doing this a little fast because I really want you to think about this on your own. So these remaining 2 entries, observe that the total sum of all these numbers had better be 24, because the total number of permutations of 1 2 3 and 4 is exactly 24. So observe total permutations, total number of permutations is 24. So here I have 6 8 6, and let me just fill these remaining 2 numbers, and you should work these out to see that you get exactly these numbers. This is a 3 and the last one is a 1. Okay. So a 6 8 3 6 1, let us check, it is 24, that is 14 plus 3 17 23 24. Okay. So these are the various numbers of permutations of various cycle types. So observe, this is a somewhat finer counting of the set of permutations. The total number is just counted very easily, it is 4 factorial, but when you want to get a finer idea of how many have cycle type 4, how many have cycle type 3 and 1 or 2 2 and so on, then you need to sort of use these ideas of circular permutations and first choosing the entries and things like that. Okay. So it is a slightly more sophisticated counting problem which brings in many of the techniques we have looked at so far. Okay. So next time we will do a little bit more about permutations specifically related to cycle types and the notion of sign of a permutation.